Hello and welcome to Easy Maths. In this video, we're going to focus attention on the area of chords again as we continue going through the concepts that have to do with chords in the topic of circles, chords, and tangents. And so let's just turn to the day's lesson. Intersecting chords. Normally, intersecting chords form pairs of similar triangles, and they could intersect internally, like in the case we are dedicating this lesson to, and in the next lesson we're going to be looking at chords that are intersecting externally. Now, consider the circle we have there. We have the chord AB intersecting with PQ at the point M. Now, there is a chord AP, a dotted chord there, and another one there. Now, the angle APM equals to QBM because they are subtended by the same chord AQ. Look, we have the chord AQ subtending the angle APM. So this angle here, APM, subtended by that chord AQ, and yet AQ also subtends the chord QBM, that chord there. What's the reason? At this point, students should be familiar with the fact that angles subtended by the same chord on the same segment are equal. Similarly, PAM should be the same as BQM because of the same reason. They are subtended by the chord PB. Additionally, AMP should be equal to QBM because they are vertically opposite angles. AMP, see, AMP, this angle here is the same as this other one here because they're just formed by two lines which are crossing each other. So they are vertically opposite angles, and therefore they're equal. If that is true, triangle AMP is the same as the triangle QMB, sorry. The order of the letters really matter at this point. These two triangles are congruent, and if they are, we can say AM divided by QM should be the same as MP divided by MB. Notice that AM and QM are the first two letters before and after the similarity sign, and MP and MB are the last two letters before and after the similarity sign, respectively. Again, if this is true, we can cross multiply and get this sort of an expression. AM times MB should be the same as QM times MP, and this is a concept that we are targeting to get. If two chords are intersecting internally, they form similar triangles, by which case we can get this sort of an equation. And therefore, whenever we are given a length, say we are given AM and PM and MQ, we can be able to get the length MB. That is what we are dedicating this lesson to. Now, similarly, the triangle AMQ is also congruent to PMB because of reasons that are the same as this. There are two angles which are subtended by the same chord. I think the angle at A, and the angle at P. There is this chord BQ subtending an angle at P and another angle at A. And so we have a similar triangle, two similar triangles like this. You can try to prove using the same angles that I've used in the first scenario there. And if this is true, then again we say AM divided by PM should be the same as MQ divided by MB. Notice that AM and PM are the first two letters of before and after the similarity sign, AM and PM, and then MQ and MQ and MB. Cross multiplying, we get the same thing we had earlier. And again, if we write AM divided by MQ like this, the first two letters, last two letters before the similarity sign, and again the first two letters and last two letters after the similarity sign, and cross multiply, we still get the same thing. And that tells you that if two chords are intersecting internally, then we can get the fourth dimension if we have three dimensions, as I said earlier. We turn to an example. We're told find the length kx in this diagram here, and we know that wk times kx should be the same. Wk times kx should be the same as yk times kz. We don't have kx, and therefore 4 times that unknown that you don't know there is the same as 5 times 1, and therefore kx is 5 over 4, and the answer therefore is 1.25. And that brings me to the end of that particular lesson. Check out the next video, which is posted also at the same time with this, circles intersecting externally. Always like, subscribe, and share. I'll appreciate it. Thank you.